Welcome to solverfy.
We know that we're dealing with helium atoms, and we can say that for part A, the average de Broglie wavelength, we can say lambda average would be equal to the Planck's constant divided by the average momentum. This is going to be equal to Planck's constant divided by the square root of 2 times the mass times the kinetic energy average. And this would be equal to, we can say h divided by the square root of 2 times the mass times 3 times Boltzmann's constant times the temperature over 2. And we can rewrite this and say that the average wavelength would be equal to Planck's constant times the speed of light divided by 2 times mc squared divided by kt. And at this point, we can say that here, my apologies, at this point we can say that the average wavelength would be equal to 1,240 electron volts nanometer, and then this would be multiplied by the square root of 3 times 4 times 938 mega electron volts, and then this would be multiplied by, rather divided, my apologies, by 8.62 times 10 to the negative 5th electron volts per Kelvin, and then divided by, rather multiplied by 300 Kelvin. Extend the square root. And for part A, we find that the average de Broglie wavelength would be equal to 7.3 times 10 to the negative 11th meters, or we can say 73 picometers. We can then say for part B, the average separation would be equal to 1 over the third root of n. And this would be equal to 1 over the third root of the momentum divided by the Boltzmann constant times the temperature T. So this would be 1.38 times 10 to the negative 23rd. This would be joules per Kelvin, and then multiplied by 300 Kelvin. And then this would all be divided by 1.01 times 10 to the 5th pascals. My apologies. This isn't, I said that this was momentum. This is not momentum. This is actually pressure. My apologies. And we can then take the third root, or we can say this entire term to the 1/3 power. So taking the third root or setting it to the 1/3 power, of course, this is going to be the same answer. And the average separation is found to be 3.4 nanometers. This would be our answer for part B. And then finally, for part C, the question is asking us, can the atoms be treated as particles under these conditions? And yes, atoms can be treated as particles because the average de Broglie wavelength is much less than the average separation. And that would be the condition for them to be treated as particles. That is the end of the solution. Thank you for